Hello everyone. In this video we are going to get introduced to the Pde or proportional derivative controllers and then to the lead compensators, and we see that the main aim of using these controllers is to improve the transient response. So our focus will be on improving the transient response. If you remember, in the previous videos we were using the Pi and lag compensators in order to improve the steady state behavior of the system. So let's see what a Pde controller is. It's composed of two parts, a proportional part and a derivative part. Through the derivative part, the control action will be proportional to the error through a derivative of the error indeed. Okay, so our control action will be proportional to the derivative of the error through a constant Kd, and with the proportional part the control action will be proportional to the error itself through a constant Kp. So actually for our proportional derivative or Pde controller, we can write the output of the controller u of t, which is the input to the plant, being equal to Kp times the error plus Kd times the time derivative of the error e dot of t. And in the Laplace domain, as the transfer function, we can write u of s is equal to Kp plus Kd times s times e of s. Or in other words, the transfer function for the controller u over e will be equal to Kp plus Kd times s. And it could be alternatively rewritten in the form of k times s plus zc, where k is equal to kd and zc is equal to kp over kd. So please pay attention that k, the gain of the controller in this form, will be equal to kd, and the location of the zero of the controller, zc, will be equal to kp over kd. So basically, for the ideal Pde controller, we will have a single zero and there are no poles. That's why it is called an ideal controller, because in practice we cannot have such a controller. So the zero of the controller will be located at minus zc, which is minus kp over kd. And then obviously if we keep kp fixed, with the low value of kd, if kd is low, then is small, then 0 will be far from the origin. If the value of kd is high, then the 0 will be close to the origin. So as kd increases, 0 moves towards the origin, and as kd decreases, 0 moves far from the origin once kp is fixed. You should also notice that the derivative action gives an anticipative action, similar to what we had with the addition of the zeros to the system. So we already have analyzed how the additional zero will change the step response of the system, and over there we have seen that zeros have some anticipative, they add some anticipative behavior to our system. And that's true over here as well, because the controller which is added to the system is indeed in the form of an additional zero. If the error is growing fast, then the controller will tend to make it decrease immediately, because the control action is proportional to the derivative of the error as well. So if the error grows fast, then its derivative will be big, and then the control action will become bigger. However, with this Pde controller, we have three main problems. The first thing is that the controller is an ideal one and it is not realizable in practice. So we cannot create such a system in practice, or such a controller in practice. The second one is that it would generate spikes in the control action u of t every time that r, and therefore e, because E is equal to R minus Y has a discontinuity. So if you have a step input, let's say, once the reference signal has some discontinuity in the form of a step, let's say, over here at that point, since the error will be also discontinuous, and since we are taking the derivative of the error, there will be spikes for u of t right at that moment, which is a problem, yeah, because in that case our equipment might be damaged. The third problem that we have is that this kind of controller tends to amplify high frequency components. As the controller is taking the derivative of the error, if there are high frequency components, their derivative will be high in terms of the magnitude, and then they will become amplified more. An example of such a high frequency component would be the sensor noise. So Pde controllers are not good in dealing with the sensor noise. For all these reasons, the ideal Pde controllers wouldn't be used, but for the moment, let's assume that we can implement it, and let's see how using this kind of controller would be beneficial for us using the Root-Locus. Let's see how the effect of the Pde controller would be on our system. As I just mentioned, we already have discussed the effect of an additional 0, and it introduces some anticipative behavior to our system. On the other hand, a 0 in the controller, and therefore in L, because L is equal to Gc times Gp, if we have a 0 in the controller, that 0 will appear in the loop transfer function, and it will also appear in the closed loop transfer function. Because for T of S, we have L over 1 plus L of S. And if you have a 0, in the loop transfer function, it will appear in the closed loop system as well. And as a result, for our closed loop system, we will have the anticipative behavior, and the step response of the closed loop system could be also made faster. In other words, we can decrease the settling time. Decreasing the settling time means that we are indeed making the response faster, while we maintain the same MP, or we can decrease the MP while keeping the same settling time, or even decreasing the settling time. In general, a 0 on the negative real axis will also tend to move the Root-Locus towards the left-hand side, towards the minus infinity, in other words. And therefore, it could also help to improve the stability characteristics of the system. As an example, over here we have a system without a 0. So there are indeed, let me just choose the proper size for my pen. Let's assume that we have 2 poles here and there. If I draw the Root-Locus plot for this system, it will be similar to this. So for some values of k or rho bigger than k star, the system will become unstable. But now, if we introduce a 0 to this system, let me just redraw it. We have the same poles, and now I introduce a 0. Let's put the 0 here. Now if I draw the Root-Locus for the system, one branch will be here, another branch will be here, and now you can see that for some values for k bigger than k double star, we will have the closed loop system stable. for a range of values of k, our system will become stable, while in the for the case without the 0, which could be the 0 of the controller, the range of values of k in which the system was stable was quite limited. So by addition of the 0 properly, we can make our system stable. But you should pay attention that we are saying that by proper choosing of the location of the 0, because if we don't do it properly, let's say we add the 0 over here, we make our system always unstable. You can see that we have always a pole over here all the time. So you should pick the place for the 0 properly in order to make the system stable. But that's a property that could be obtained. Now over here, let's go through an example. We have the type 0 system with 3 poles at -1, -2, and -5. First, we consider a proportional controller to achieve this value of zeta 0.4. And for that, if you can indeed apply the RL tool in order to obtain the exact value for the controller, which will be equal to 23.72. So with that value of the proportional controller, the closed loop poles will be located in the form of complex conjugate in those places, and the third pole will be over here as well. So on the real axis with the value of around -6.5. For the dominant pair of poles, we will have zeta equal to 0.4, which is what we are looking for. Okay. Now for this controller, for this system with this proportional controller, the settling time for the step response is equal to 4.26 seconds. You can obtain the value for zeta omega n. It's already given over there, 0.939, 0.939. And then you can apply the formula that we have for the underdamped second order system. Now we will see how addition of a 0 will change the situation. So let's say that we are happy with the damping ratio zeta, which will give us the overshoot of 25.4%, but we want to have a shorter settling time. So we need to have the settling time shorter. And if you keep in mind what we had for the settling time, it is proportional with 1 over zeta omega n. So if we want to make the settling time smaller, if you want to make this smaller, we need to increase the value for zeta omega n. And increasing zeta omega n means that we need to move the dominant poles of the closed loop system more towards -infinity. So we need to shift the position of the closed loop poles of the system towards -infinity. And obviously we cannot do this using only a proportional controller, because if you look here, if we change the value for the proportional controller, increasing it, we will move in this way, decreasing it, we will move in this way, and in both cases, the requirement on the zeta will not be satisfied. We need to keep the proportional value of the controller equal to 23.72 in order to satisfy that. And by moving the value of the proportional controller, we cannot satisfy, or we cannot change indeed the settling time by keeping the same overshoot or damping ratio. Okay, so now we can think about using an ideal Pde controller, which is defined as k times s plus zc, where we can place the 0 of the controller at different places. In this example, we will put it at -4, -3, -2, and then we will adjust the value of k in order to get zeta equal to 0.4. For those three cases, we have the Root-Locus diagram plotted here. In the first case, the 0 of the controller is located at -4. It is over here. And you can see that, first of all, the Root-Locus is changed, obviously. But in terms of the transient requirement, one of our transient requirements was to keep zeta equal to 0.4. And by proper choosing the value for the gain of the controller, which is k equal to 20.76, we are satisfying that. Okay, so zeta equal to 0.4 is there. We have two poles here and there, and the third pole is here at -4.5 almost. And if we will see how the settling time is improved. Over here we have the numbers, but let's see what happens when the 0 of the controller is located at -3. When the 0 of the controller is located at -3, again the Root-Locus is changed. We have, by proper choosing of the value of the gain of the controller, we can place the pose still satisfying these requirements, zeta equal to 0.4. One closed loop pole will be located at -2.437 plus J 5.583, and the other one will be here, the conjugate of that pole. And the third pole will be located over here at -3.8 almost, okay, close to -4. And in the third case, we have the 0 of the controller exactly on the pole of the system. So the pole at -2 for the system is cancelled by the 0 at -2. The Root-Locus is changed. Now the Root-Locus is indeed similar to what we have here. And now by proper choosing of the value of the gain of the controller, k equal to 51.25, we are satisfying the requirement on zeta. We can have a look at what we get for the settling time for these three cases. Settling time is equal to 2.14 seconds when 0 is at -4. It's equal to 1.64 seconds when 0 is at -3, and it's equal to 1.33 while the 0 is at -2. In all those three cases, we are satisfying the requirement on zeta, and you can see that as the 0 moves towards the origin, from -4 to -3 and then to -2, the settling time is improved more. Initially, without the additional 0, the settling time was equal to 4.26, and now by the addition of the 0 of the controller, the settling time is improved. In general, when you want to design a Pde controller, so it's not in these slides, but I will explain it here. The method for designing the Pde controller is like this. You determine the desired location for the closed loop pose of the system. For closed loop pose, with the controller we have only a single 0. It's equal to k times s plus zc. Once we know the desired location, you need to apply the phase condition, and then with the phase condition you will get the value for, I call it phi c, the angle contribution, the desired angle contribution from the 0 of the controller. I might show this later with an example, okay? Once we have the desired angle contribution from the 0, once it is given, it is found, we can determine the value for ZC. ZC will be determined. And once ZC is determined, we can tune the value of K in order to place the closed loop pose at the desired locations. So, and then we will have the closed loop, the controller, the ideal controller for the closed loop system. Let me show you an example. Let's assume that this is our system. We have, I'll give you a simple example. So we have two poles here and there at -1, at -3, for which you can easily draw the Root-Locus. This is -2. And now let's assume that in order to satisfy the transient requirements, we need to place the poles at, let's say, at 2 plus J2 and -2 plus J2 and -2 minus J2. Okay, so this distance is 2, -3 indeed, -3 plus J2 and -3 minus J2. And obviously with a proportional controller it is not possible. Then we say that let's introduce a 0, so the 0 of the controller will be placed somewhere like this. Let's apply the phase condition. The phase condition will say that phase of n minus phase of d will be equal to phase of -1 over rho. For phase of n we have only the 0 from the controller, so this is phi c. We will have phi c minus the contribution from the pose will be in the form of θ1, which is 90 or pi over 2, plus the angle that we have here, I call it θ2. You can easily find the exact value, and it should be equal to, for the positive locus, it will be equal to h plus 1 times pi, where h could be equal to 0 and this will be equal to pi. So after this you can find out the value for phi c. Okay, phi c will be determined, and once we know phi c, we can determine this value for zc. And then once we have the value for zc, you can apply the amplitude condition in order to determine the value for the gain of the controller, or kb. And once you find it, you will have the controller in the form of k times s plus zc. So that's basically the way in which you can design the Pde controller using the Root-Locus approach. But since we know that the Pde controller is an ideal controller and we will not use it in practice, in the next video we will see how we can make it more practical by using the lead compensators, which will include the 0 of the controller plus a pole of the controller in order to make it practical. We will discuss that in the next video. So for this video, we are done in it. Thank you for watching and see you in the next video.